Kohlrausch's law of independent migration of ions. Now, this states that at infinite dilution, each ion contributes independently to the total molar conductivity of an electrolyte. That means if I say that at infinite dilution, that means concentration tends to zero. When concentration tends to zero, then each ion contributes independently to the total molar conductivity of an electrolyte. That means lambda m at at infinite dilution, that means lambda m naught when C tends to 0. So this will be equal to the lambda naught for the cation plus the lambda naught for the anion. So here capital lambda m stands for limiting molar conductivity for the electrolyte, and this is lambda plus naught. That means what? Contribution of the cation to the molar conductivity, and lambda negative naught is the contribution of the anion to the molar conductivity, and this occurs at infinite dilution, that is concentration C tends to 0, so it has the limiting value. And nu plus and nu minus, they are total cations and anions formed on dissociation of the electrolyte. For example, if I take NaCl, it is a strong electrolyte and it dissociates completely to Na plus 1 mole, Cl minus 1 mole. So lambda naught of Na plus molar conductivity of the cation plus the molar conductivity of the anion. That gives the total limiting molar conductivity of NaCl. Now, for strong electrolyte, the linear plot, it decreases with root C. So that is what is observed when I take KCl. This is the nature. It decreases gradually. Concentration is decreasing. But keep in mind that what is happening, the lambda m is increasing when the concentration is decreasing. And it is a straight line graph. And here this is the Debye-Huckel-Onsager's equation. This is your Debye-Huckel-Onsager's equation, and in this equation it is formed on account of the nature of the plot obtained for strong electrolyte. If I extrapolate this plot, extend it backwards, then I will get the limiting value, which is the lambda m naught, where concentration is 0. Okay, and so we can get the lambda m naught value for strong electrolyte graphically, right, by extrapolation. But for weak electrolyte, see this region, what happens near the concentration tending to 0, the plot goes parallel to the y-axis and almost it runs parallel throughout. It will never meet to give you the lambda m naught value graphically. So for those cases, we use Kohlrausch's law in order to calculate the lambda m naught using some strong electrolyte, right? So lambda m naught of acetic acid, CH3COOH, this is a weak electrolyte, and this dissociates completely to give you what? Lambda naught for CH3COO minus plus lambda naught of H plus. But this is obtained, the value is obtained with the help of strong electrolyte. Like CH3COO minus, this will be obtained from lambda m naught of CH3COO-Na, where you will get what? You will get lambda naught of CH3COO minus plus lambda naught of Na plus. This you are getting. and you have to get H plus, right? So again you use a strong electrolyte HCl. So from here you get what? Lambda naught of H plus and lambda naught of Cl minus. So what you needed you have actually got. You needed CH3COO minus, you needed H plus. Now in this you have added Na plus and Cl minus, so you can do minus lambda m naught of Na plus and Cl minus, that is NaCl. So when you do this you will get the value of lambda m naught, the limiting molar conductivity of acetic acid, which is a weak electrolyte, with the help of the limiting molar conductivities of the strong electrolyte using Kohlrausch's law. There are other applications also from Kohlrausch's law. And what are those applications? Calculation, this was the calculation of the molar conductivity of weak electrolyte at infinite dilution. So what you have done, you have calculated the molar conductivity of weak electrolyte acetic acid over here using strong electrolytes HCl, sodium acetate and NaCl, right, at infinite dilution. Next, what are the other applications? The next application is determination of degree of dissociation. So, determination of degree of dissociation. So, degree of dissociation of weak electrolyte. So degree of dissociation of weak electrolyte can be given by alpha for weak electrolyte. Okay, so it can be given by alpha. And what is the formula? Alpha is equal to the molar conductivity at any concentration C divided by the molar conductivity at infinite dilution. Next is the determination of dissociation constant. Determination of dissociation constant K. Dissociation constant K of weak electrolyte. Now this is again another application. How? If I say alpha is the degree of dissociation, then K for weak electrolyte is C alpha square by 1 minus alpha, right? And we know alpha is equal to lambda m concentration C by lambda m naught. So you can just place it. You can say C into lambda m concentration C by lambda m naught. This is whole square divided by 1 minus lambda m C by lambda m naught. So this is by placing. Another application is determination of solubility of sparingly soluble salts. Of sparingly soluble salts. What are sparingly soluble salt? Sparingly soluble salts are those salts which are partially soluble, not completely soluble. We know lead salts are partially soluble. There are many other salts which are partially soluble. For them, we can find the solubility using this formula. Lambda m naught is equal to kappa into 1000 by C, which is the molar concentration. So I can say molarity. Okay, so this can be actually substituted by its solubility, because how much of the solute is getting dissolved, that is the solubility. So we can write divided by solubility. So we can find solubility using this formula, that is kappa into 1000 by lambda m naught. So these are the applications of Kohlrausch's law.